तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, today we shall continue our discussion on the 7400 TTL gate. I will draw the circuit once again. This is the earliest form of the TTL gate, okay, and it is important to understand the circuit, how it works, and then once we understand this, we can look at the modifications. We can very easily understand the modifications in the later stages, in the more advanced versions of this gate. So, this TTL always uses 5 volt power supply. These are the resistance values. Okay. This is the TTL NAND gate 7400. Okay. So, what we shall do first in today's class is we shall obtain the input output characteristics of such a gate. Okay. This is the output point, okay, and we shall take the input at one of these, we shall take one of these inputs as the input to the circuit. All right. Now, before actually going into the input output characteristics, the better way to do this is to consider this input here at the base of T2, all right, of the transistor T2, and obtain the characteristics of the output voltage versus the voltage at the input of or at the base of T2, that is VO VB2 characteristics. Once we do that, then we can very easily get the input output characteristics by obtaining the drop across the, if you know what is the drop across the T1 transistor, all right. So, now let us see what is the characteristics like. Okay. So, all right, now let us see when VB2 is say 0 volts, okay, all right, then what happens to T2? T2 is off obviously because the base voltage is small, and if T2 is cut off, T3 will be also cut off, okay, because there is no emitter current for this, and if there is no emitter current, T3 cannot have any base current. So, T2 and T3 is cut off, okay. And what about T4? Because there is a base current for T4, T4 will be on, okay. And so, what is going to be the output voltage? Now, the output voltage would be the drop across output voltage will be, so when I should write when VB2 is equal to 0, V output will be equal to VCC minus I should call this IB4, okay, this current which is the base current of T4, IB4 into 1.4 kilo ohm minus VBE4 minus 1 diode drop, okay, all right. Now, so we know all this, VCC we know 5 volts, these we can assume to be around 0.7 volts, okay. Now, this voltage drop, if you assume say that the load is it depends on the load current actually, how much current you are drawing, okay, which is the emitter current of the transistor T4. Say if you assume that this load current is 1 milliampere, okay, and if the beta is 50 of this transistor, then the base current is around 20 microamperes, all right. And 20 microampere into 1.4 kilo ohm would be 0.02 into 1.4, that is around it's less than 0.1 volts, okay, all right. So we can almost neglect this term, okay, all right. So it is almost equal to, if you assume 0.7 volts each, okay, this is almost equal to 3.6 volts, all right. So when VB2 is equal to 0, output voltage would be around 3.6 volts. Okay. Now, how long does this output voltage remain at 3.6 volts? As long as this situation prevails, okay. We can say that this situation is going to prevail as long as T2 is cut off, all right. Now, if we say that the T2 the base input voltage at which T2 starts base current starts to flow at T2 is around say 0.65 volts or something, okay. Then we can say that when VB2 till VB2 is 0.65 volts, okay, this output voltage will remain at 3.6 volts, okay. So if we then we can draw like this, okay. So this is 0.65 volts, okay, all right. So the same situation prevails, okay. So we can say, I'll just write it here, when VB2 is less than 0.65 volts, okay, T2 and T3 is off, are off, and T4 is on, okay, all right. And that is why you get V output is equal to 3.6 volts, all right. Now what happens when it exceeds 0.65 volts, say when this input exceeds 0.65 volts VB2, this transistor T2 is going to start conducting, all right. And when T2 starts conducting, this part of the circuit, okay, which I called it the phase splitter part, okay, this behaves as a amplifier, okay, with a gain of minus RC by RE, you know that, okay, an amplifier, okay. So that is 1.4 by 1, that is 1.4. So the voltage at this collector point, okay, is going to fall, okay, is going to have a gain of minus 1.4 with respect to the base voltage, okay. So as the base voltage keeps on increasing, this voltage falls by 1.4 times that, okay. And since this point here is basically the emitter follower point of this transistor, okay, this is also going to follow, all right. That is, the output voltage here is also going to have a gain of minus 1.4 with respect to VB2, because this voltage is 0.7, they remain almost constant, they do not change, okay. So as we go on increasing the base VB2, this output voltage is going to fall with a slope of minus 1.4, okay. And how long is that going to happen? Till the point, okay, till T3 starts conducting, okay, all right. Now what is this voltage range in which T2 is on but T3 is off, okay, all right. Now as we go on increasing this voltage, what is going to happen is this voltage is falling but this voltage is increasing, okay. That is the base voltage of T3 or the emitter voltage of T2, that voltage is increasing because that is the emitter follower point, okay. So if we say that 0.65 volt is the cut-in voltage, so when this voltage becomes 0.65, that is at the base of T3, this T3 is going to turn on, okay. And then if we say that at that point T2, the base voltage of T2 is 0.7 volts, okay, because it is conducting, okay. So this is 0.7 volts, VB2 is VBE2 is 0.7 volts. Then we can say that when VB2 is 1.35 volts, because this is 0.7 and at the base of T3 is 0.65. So when I can write here, when VB2 lies between 0.65 and 1.35 volts, okay, T2 is T2 and I'll say T4 is on T3. Okay. All right. So at this range, what is the output voltage? The output voltage falls with a gain of minus 1.4. Okay. So this one, in this range, you know, when VB2 becomes 1.35 volts here, okay, this is going to fall okay. So this is 0.7 volts difference, okay. If the slope is minus 1.4, okay, this would be around 1 volt, okay. So this is 2.6 volts, okay. All right. Okay. Now what happens? This has become 0.65 volts, and now if you go on increasing VB2 even further, all right, this output voltage will fall with the slope is going to increase even further. Why? Because if you look at this amplifier now, okay, this transistor, okay, input of this transistor is coming in parallel with this 1 kilo ohm, all right. And so what happens is effectively the emitter resistance is going to be reduced, all right, and so the slope is going to be increased, all right. Okay. So the output voltage is going to fall more sharply, okay, and so both T2 and T3 are is conducting. So what is going to happen is ultimately, okay, because T3 gets its base current from the emitter current of T2, all right, mostly part of it is of course bypassed, but most of it flows in as base current of T3. T3 is going to go to saturation, okay, before T2, all right, because the base current is much larger in the case of T3 because it's derived from the emitter current of T2, which is, okay, I mean, all right, you understand. So it's a large base current. So T3 in fact goes to saturation before T2, okay, all right. So at around VB2 is equal to 1.4 volts, okay, 1.45 I should say, if you say that it is the saturation at saturation VB is 0.75 volts, okay, okay, it's 0.75 and 0.7. So at around 1.45 volts, okay, T3 goes to saturation, and when T3 goes to saturation, what is the output voltage? It's 0.2 volts, okay. So there is a very sharp fall, you can see it actually goes down like this, okay. At 1.45 volts, okay, this is 1.45 volts, the output voltage has reached 0.2 volts, okay. This is 0.2 volts, all right. So, okay, and now of course if you go on increasing VB2 even further, okay, this at 1.5 volts, if you assume that 0.75 volts is the base emitter voltage at which the transistor goes to saturation, okay, at 1.5 volts T2 also goes to saturation, okay. So it's just, you know, it keeps on like this, but you must understand the fact that okay, VB2 you are not applying VB2, this is not, there is no external voltage source, and VB2 cannot exceed something like 1.5 volts, okay, because it would mean that the base emitter drop of a forward bias junction, okay, is very high, which is not possible again, as we said, okay. So this, if you plot the V output VB2 characteristics, okay, you must have to truncate it here, all right, because this voltage is cannot go more than that, all right. Okay, is it clear? So what happens? The V output VB2 characteristics. Okay, so this is this characteristics. Now what we are going to do is we will try to translate this VB2 axis, okay. We would basically like to draw the corresponding V input axis, okay, and see what is this value, okay, what are these values on the V input axis. Okay, so what I mean is that when VB2 is 0.65, what is VI? When VB2 is 1.35, what is the value of VI? All right, and then we will have the input output characteristics. Okay, so basically we have to understand the state of this transistor T1, that is the multi emitter transistor here. Okay, all right. Okay. Now when Vi is quite large, okay, when Vi is quite large, I mean the input voltage is quite high, I should say, okay. What is the state of this transistor? This transistor is acting in the active inverse mode, you know that we have already discussed, and this base current flows into T2, of course, and this T2, this VB2 will be at around 1.5 volts, okay, and this output voltage is going to be 0.2 volts. Okay, so when V input is quite large, okay, you have output voltage is 0.2 volts. Okay, now suppose you are reducing V input from a very high value, okay, what we want to know is at what value of Vi, okay, does this say T2 start coming out of saturation, okay, all right, because T2 will come out of saturation before T3, okay, because we have already said that T2 goes into saturation later than T3 when you are increasing the voltage, okay. So when you reduce the voltage, this T2 will come out of saturation first, okay, and then T3. So at what value of input, okay, does this T2 come out of saturation? That is when somewhere around this point, okay, this 1.5 is where the transistor goes to saturation, okay. So let us look at that. Now let us assume again that when T2 is just at the edge of saturation, okay, that VCE of this transistor is almost around say 0.3 volts, okay, it's very close to 0.2 volts, say it is 0.3 volts, okay, all right. And and what is this voltage? This transistor is in saturation, so here it is 0.75 volts, okay, all right. So what we want to know is what is the collector current of T2, or what is the current which is flowing here, okay. So we can write, so if you want to calculate the collector current of T2, IC of T2 at that under that condition, okay, then IC of T2 we can write is equal to 5 minus 0.75 minus 0.3, okay. 0.75 is the voltage at the base of T2 and 0.3 is the drop across T2. So that is the drop across the 1.4 kilo ohm resistance. So this is the collector current of T2. This is around, you can say 1 volt, so it's 4 by 1.4 kilo ohm, okay. So this works out to be around how much? 4 volts by 1.4 kilo ohm. Okay. So, it is around I think 2.8 milliamperes, because 1 by this is okay, 0.7 into 1.4 is 1. So, it is okay. So, it is around 2.8 milliamperes. Okay. So, what is the base current of T2, which is actually equal to the collector current of T1. Okay. So, this is going to be this divided by beta, all right. So, if you assume a beta of 50 say, okay. So, this is going to be 2.8 milliampere by 50, okay, which works out to be 56 microamperes. All right. So, what is happening is, at that point of time, a current of 56 microamperes is flowing into the base of T2, all right. Okay. And what is the base current of T1? That is, if you assume this is 1.5 volts, okay, around 1.5 volts, and this junction is also forward biased. So, this voltage can at the most be 2.2 volts say, okay. So, you have a 0.7 milliampere of base current flowing, okay. So, in this transistor, a base current T1 transistor, a base current of 0.7 milliampere is flowing, and a collector current, okay, that is a reverse collector current basically, okay, negative collector current, okay. Normally in a normal transistor, a collector current would flow into the collector, okay, in an NPN transistor. So, a very small negative collector current is flowing, all right, of 56 microamperes, very much smaller compared to the base current, all right. And then what happens, if you go on reducing the input voltage even further, what is happening is slowly that even that 56 microampere is going to reduce, and finally it will be a 0 current, that current goes to 0, all right. The collector current of T1 reduces and finally goes to 0, and this T2 is cut off, all right. So, if you look at this region of the characteristics, okay, at this end, when the T2 is just at the edge of saturation, a very small collector current, a negative collector current is flowing, all right. And as you reduce the input voltage, okay, or all right, what is happening is that negative current goes to 0, okay. So, at what region of the characteristics is this transistor operating? Okay. You have to recall our discussion on the bipolar transistor characteristics, okay, and I had referred to one particular region of the characteristics, okay, and said we are going to discuss it, or we are going to come back to it when we discuss TTL, okay. All right. So, if you look at the transistor characteristics, okay, we usually draw it like this, you know, but I said if you magnify this region, all right, it is actually it is something like this. The characteristics actually start off something like this, and this region is called the offset region, okay. So, this is VCE, this is output characteristics, I see, okay, all right. So, in this region IC is negative, okay. So, negative, and then it slowly goes to 0. So, basically IC goes to 0 at a small positive VCE, which is called the offset voltage of the transistor, okay. And we have also seen the reason for that when we discussed the bipolar transistor, okay. So, basically what is happening is it is operating in this region. So, a small negative current of 56 microampere which goes to 0. So, it is almost confined to a small region here, okay, throughout the entire operation of this region, okay. For T1 it is confined in that region, okay. So, approximately we can assume that the drop across the VCE of T1, okay, is around 0.1 volts, okay, along for the entire region here, okay, approximately. It's a very small voltage, around 0.1 volts say, okay. Now if VCE is 0.1 volts for T1 in this entire range, okay, so what is going to basically we have to translate or shift this axis by 0.1 volts to get the input output characteristics, okay. Of course it is going to change by a small amount, it is not constant, but it is almost a constant, okay, it changes by a very small amount because this entire range is very small, okay. So it is around 0.1 volts and it goes like this, okay. So if you look at it like that, okay, it is just a very it is a very small region. So what you have here is this 0.65 will become 0.55, okay, 1.35 would become 1.25, 1.45 would become 1.35, so on, okay. And of course when you draw the input output characteristics, you are not constrained here, you can go to high voltages, all right. Is it clear? So basically if I draw the input output characteristics, okay, what I am going to do is this remains the same, I am just going to make this Vi now, okay. I just make this 0.55, this is 1.25, this is 1.35, and this can go on, because as you increase the input voltage, okay, this transistor this remains in saturation, okay. So all right, and the output voltage is 0.2 volts, okay. So this is the input output characteristics of this TTL gate, all right, okay, fine. Now well yeah, okay, the next thing we shall see is about some further specifications of this gate, okay. Now if you look at this manual of this 7400 gate, okay, and look at the different specs of this gate, okay, you will come across the values, okay. These terms we have already defined, VIL, VOL, VIH, VOH, okay, you know what they are in terms, okay. VIL, the values which are given is VOL is 0.4, this is 0.8, V output 2.4 volts, and this is VIH is 2 volts. So these are the specifications provided by the manufacturer, all right, which means that V output low, okay, the maximum value the output can have when it is output is low is 0.4 volts, okay, and V input low, that is the maximum value of the input which will be considered a logic low is 0.8 volts, okay, it is somewhere here, all right, okay, 0.8 volts, and but the thing is they define VOH as 2.4 volts, not 3.6 volts, because if you define VOH as 3.6 volts, okay, you would have to define VIL as 0.55 volts or even less, okay. So now so actually this, if you look at these specifications, you will find that they are very conservative in the sense that one could, if you look at the characteristics, give a better description, in the sense that you could say you could put VOH at a much higher value and so on and so forth. But why they do it is that they manufacture a large number of chips in a batch processing, and if they give very stringent conditions, they will have to reject a lot of their output. So these values are more conservative, okay. Now so they say that VOH is VIL is 0.8 volts and VOH is 2.4 volts. It means that if the input voltage is less than 0.8 volts, they guarantee output voltage greater than 2.4 volts, and if the input voltage is greater than 2 volts, the output voltage will be less than 0.4 volts. Okay? And we see that is going to be satisfied by this characteristics, okay, because at 0.8 volts, okay, output voltage obviously is going to be greater than 2.4, and at input voltage greater than 2 volts, output voltage obviously is going to be greater than 0.4 volts. And what does this mean in terms of noise margin? The noise margin definitions, I hope you remember. Okay. So, the noise margin, high noise margin is given by 2.4 minus 2. Okay. This means that noise margin high is 0.4 volts and noise margin low is also 0.4 volts. That is another reason for giving this type of specifications, because there is no point making one noise margin high and the other very low. Okay. So, these are the one part of the specifications. You will also find another set of specifications which is terms of current. Okay. You will this is IIL, IIH, IOL, IOH. Okay. IIL is the input current when the input is low. Okay. For this it is 1.6 milliamperes. IIH is 40 microamperes. Okay. IOL is 16 milliamperes and IOH is 0.4 milliamperes. Okay. So, these are another set of specifications which is given. Now, IIL is the input current when the input is low. Okay. It is the maximum value. Okay. It is the maximum value of the input current when the input is low. Okay. So, the input current can be at the maximum 1.6 milliampere. Okay. IIH is 40 microampere, is the maximum value, okay, of the input current when the input is high. So, obviously, you will see that if you go back at this circuit here, okay, when input is low, say 0.2 volts, this would be 0.9 volts, okay, which would mean actually a current of 1 milliampere, which is the same as since this transistor collector current is almost 0. So, base current is almost equal to the emitter current. So, a current would flow in this way equal to slightly greater than 1 milliampere. But of course, they give a somewhat higher current, because you know this in IC technology, the resistances cannot be fabricated with such definite values. Okay. There is always a tolerance. Okay. So, if the resistance is much less than 4 kilo ohm, okay, the current is going to go up. Okay. So, they say that the maximum input current, okay, when the input is low is 1.6 milliamperes. On the other hand, when the input is high, all right, this transistor is operating in the inverse mode. Okay. And the collector current, which this behaves as the collector in the inverse mode, and the collector current which is flowing is actually beta reverse times the base current, which is going to be pretty low. Okay, because as I said, the beta reverse of this transistor is deliberately made very low. So, you have a very low input current of around 40 microamperes. All right. Okay. What are these IOL and IOH, the other two specifications? IOL refers to the maximum load current, okay, that the output can sink so that the output voltage is at logic low. All right. Okay. Again, I will repeat the definition. IOL is the maximum current that the output can sink, okay, so that the output voltage remains at logic low. Okay. The important thing is it remains at logic low. What is going to happen is, if you sink too much current, okay, if you look at, again I go back to this circuit here. Okay. Now, if it sinks too much current, okay, basically if you connect another gate here, you know, okay, you have say this NAND gate, okay, is connected to another NAND gates here. Okay. You have more than one NAND gates. So, this is logic low, say. All right. Now, this is the current IIL, okay, input low current which is flowing, Okay, where is it flowing into? It is flowing into this gate. So, this current is sinking, okay, the output is sinking that current. So, if you have more than one fan out, all of them is flowing in here, all right. Okay. Now, if you have too much current flowing in, you see this transistor is in saturation, okay, and the condition for saturation is that the collector current should be less than beta times IB, is not it? Now, if you have too much collector current flowing in, this transistor, you know, it can come out of saturation, okay, all right. And so, if it does that, then the output voltage is going to rise, okay. So, in order to ensure that this transistor is in saturation, okay, you have made this very high effective load, okay, but if you have too much current flowing in, basically it means that you are reducing the load, the collector resistance effectively, okay, which means that the transistor can come out of saturation, all right. So, there is a limit on the collector current which it can sink, okay, and the voltage specifications are retained, that is the output voltage remains less than VOL, okay. Similarly, IOH, okay, if you the definition of IOH is that it is the maximum current that the output can source, okay, it is the source, okay, current flowing out, okay, when the output is at logic high, so that the output voltage is maintained above VOH, okay, so that all right, that is the definition of IOH, okay, that is the maximum current the output can source when it is at logic high, okay, so that the output voltage is maintained above VOH, okay, because that is the definition of output high, that is the output voltage greater than VOH, okay. So, the manufacturer guarantees that if you do not draw more than 0.4 milliamperes when the output is high, okay, the output voltage will be retained above VOH, but if you draw more than that, it does not guarantee that, okay, that the output is going to be above VOH, okay. Similarly, for IOL, if you sink less than 16 milliamperes, output is going to be less than VOL, okay, above that it does not guarantee. So, there is no guarantee of retaining the proper logic, okay. So, this is the input and output current specifications, and they are very important to understand or the fan out criteria, okay. How many gates can you connect at the output of a particular gate, okay. So, how many? So, you have to look at both the logic low and the logic high, okay. So, you have to see, for example, IOL by IIL, okay. So, you have to take what the minimum of so the fan out, I shall write it here separately, will be minimum of IOL by IIL and whichever is minimum is going to be the maximum fan out, okay. So, in this case, of course, both are 10, so there is no problem, okay, but in many cases, especially this is very important when you are connecting two different logic families, okay. For example, you are having in a circuit, you have both CMOS as well as you are using CMOS NAND gate as well as 7400 series perhaps, okay. Now, if you are connecting, all right, you must be very careful, okay, whether a CMOS gate which you are having can drive a TTL gate, okay. You have to see, look at these current specifications, you cannot just connect them because they are NAND gates, okay, and you know that the circuit, you know, you just connect them like that, get it will work, but it does not, okay. You must be very careful of the fan out criteria. So, you have to look at, say, if you are connecting if you are connecting NAND gates like this, okay, suppose this is CMOS and this is TTL, all right. So, you must see what is the specifications, the output specifications of the CMOS gate, all right, and the input specifications of the TTL gate, okay, and you must see how many you can drive, all right. So, this is very important, this gives you an idea, okay, this type of specification. So, when you are connecting any circuit, logic circuits using these chips, okay, of different logic families. Here of course, if you buy TTL, they will give, if you have completely one logic family, maybe they will specify on the spec sheet, you know that maximum fan out 10, you are very sure. But when you have to connect different logic families, okay, you must be very careful. Okay. So, you must look at the specification sheet, okay, the currents, okay, and then only connect, otherwise you may run into problems. Clear? Okay. So, this gives you the complete specifications of the TTL 7400 series, 7400 NAND gate. All right. So, I think we have discussed this gate in great detail, and we shall move on now to the next gate in this gate in this series of the or shall I say the next series in this TTL gate family, okay, that is the Schottky TTL. So, this 7400 came out, as I said, in the mid 60s, okay, and then the next improved version of TTL which came out was the Schottky TTL series, which was the 74S00. All right, Schottky TTL series. I shall draw the circuit of this gate, okay, and then we shall list out the differences, okay, between these two circuits, and then we shall see the reasons for these changes. It is quite obvious that by the name, you know, Schottky TTL. So, this uses Schottky transistors. All right. So, and we have already studied what is a Schottky transistor. Okay. Sorry. So, I am just, this is the symbol of the Schottky transistor, as you well know. So, you will see that this looks like an S. So, there are lots of modifications which went into the next version. Okay, you can see for yourself now. I hope I have incorporated all of them. You shall see. So, well, these are the values, I think. 2.8 kilo ohm, this is 900 ohms, this is 250 ohms, 500 ohms, 60 ohms. This is of course. So, this is the circuit of the Schottky TTL 74S00 gate, NAND gate. Okay. All right. Now, if you look at this circuit, okay, we can now list out. If you we have both the circuits on the blackboard, okay, the 7400 here, and by the side you have 74S00. Now, looking at both of them, okay, all right, you can now list out the differences. Okay, all right. I can give you a hint. There are actually 6 major differences. Okay, so it's like playing a game, you know, having 2 figures and finding out the 6 differences. Okay, all right. So, can you just point out what are the 6 differences? Yes. Yeah, there are 2 diodes at the input, okay, 2 extra diodes at the input, all right. So, they are Schottky diodes. Okay, I will write Schottky barrier diodes at input. Okay, then the number 2. Yeah, there is the output transistor is okay. The one major difference, okay, I should point out is all the transistors. Okay, okay, this is also Schottky transistor. So all the transistors are Schottky barrier transistors, are Schottky transistors. Okay, except of course one. Okay, this need not be a Schottky transistor because of the fact that across the collector base junction you have this transistor, and since VCE of this transistor is also always going to be positive, which ensures that this collector emitter of this transistor is always collector to base junction of this transistor is always going to be positive. So it is always going to be in the active region. Okay, so it's not necessary. So Schottky transistors. So that is the next modification. Number 3. The values of the resistances, if you look at them, okay, they are all lower value resistances. Okay, the resistance values have been reduced, lower resistances. So all the resistances have been effectively slashed. Obviously, I shall tell you that the Schottky transistor, Schottky TTL, the focus of the Schottky TTL is to achieve higher speed. Okay, and lower resistances give you higher speed. We have already seen that. Okay, when we talked about inverter, transistor inverter. Okay, one way to improve speed is lower resistance, higher currents, which means higher currents. Yeah, what are we left with? This part of the circuit. Okay, so instead of resistance here at the base of the output transistor, you have a active. This is called active pull down. Okay. All right, you had an active pull up. So this part, okay, instead of a resistance, you have a transistor circuit here. So this is called an active pull down. Okay, so you introduce what is called an active pull down. Number 5, this one. This is, what is this configuration called? Darlington pair. And then what is the remaining one? The diode is missing, one diode is missing. Okay, missing the diode, okay, between the two, I should say. So these are the 6 major differences which you look, which you see, okay, between the two gates. Okay. Now what we shall do in the next class, we shall take up each of them. All right. See the reasons for that and what happens. How does it improve the performance? All right. So we shall take up this 74S00. Then we shall go on with the newer series 74LS, which came up later. Okay, the further modifications, okay, and then even the more recent ones, the advanced series of TTL gates, okay, which have very good characteristics. Okay, so we shall finally we'll go through the entire range of TTL series gates. Okay, and with that we shall conclude our discussion on TTL in the next class.